particular question, it says draw the orbital energy diagram, hint with a box for each orbital and an up or down arrow for each electron for the following species: a silicon atom. Include boxes for each orbital and no noble gas core abbreviations for this one. Well, our process is going to be go to silicon on the periodic table. It is element number 14. That means it has 14 electrons. The same number of protons because atoms have no charge. From there, we can go ahead and write its electron configuration: 1s2, 2s2, 2p6. And I'm doing it kind of quickly, but we are following the shape of the periodic table. 1s2, ding, 2s2, 2p6, ding, 3s2, 3p2. And I add them up: 2, 4, 6, 8, 10. Wait a minute. 3s2, 3p2. There's my 14 electrons. And I end up at box 14 in the 3p area of the periodic table. And so there's a number of little checks there to make sure that you've done this correctly. What I'm referring to when I talk about an orbital energy diagram is you start with an energy arrow, and the lowest energy sublevel is 1s. And the 1s sublevel has one orbital, and so it gets one box. And inside that orbital, you place 2 electrons. Those 2 electrons will have spin up and spin down, and so my picture right here of an arrow with half of a head, sometimes called a harpoon arrow, is going to be 1 electron with spin up and a downward harpoon arrow is 1 electron with spin down. And spin is a quantum mechanical property. We don't have to worry too much about it other than to know that these 2 electrons have something different about them and that they both fit into one orbital. And that the maximum number of electrons in any one orbital is 2. Then we go to 2s. We put our 2 electrons in there. Then following along, then it's 2p. Inside the 2p sublevel, there are 3 orbitals. These are called 2px, 2py, and 2pz. We don't designate them because we can't tell which one is which anyway. They are indistinguishable. They are also said to be energy degenerate. And energy degenerate simply means that they have the same energy. And that having the same energy is represented by being at the same position on the energy up and down scale here. There we go. Now there are 6 electrons in 2p. And the way that we fill these 2p orbitals is you put 1 electron in each of them before you ever pair any electrons. When you have to, you pair them, and we have all 6 right there. Then we move on to 3s. There is 1 box. It has 2 electrons in it. Again, we know it has 2 electrons because it's 3s2. We're using these numbers. And then when we get to 3p, the 3p sublevel still has 3 orbitals. Inside of those 3 orbitals are a total of 2 electrons. And this is important. Make sure that you put those 2 electrons in different orbitals. The reason for this is putting them in different orbitals is putting these electrons with the exact same energy, if you tried to pair them in the same orbital, one electron would repel the other into the next orbital because there's an energetic repulsion for putting them together. That's why they fill separate orbitals first. These two electrons have the same energy, but if you tried to put this second electron in the first orbital, that would be higher energy due to electron-electron repulsions, something we talk about from time to time. And this is the complete orbital energy diagram for a silicon atom. It has all the electrons going from low energy to high energy. And it shows that in 3p, there are 3 orbitals, only 2 of which have 1 electron each. Any questions about that? And we do a couple of these because...
Professor, what would have happened if you had 3p5 or 3p4?
Good question. If you had 3p4 and 3p4, say, would be sulfur, because it has 2 more electrons. So it's 3p2, then 3p3 would put an electron in this third orbital. Then 3p4 would put 1 electron going down spin in one of these orbitals. Typically, I do it from the left, but it doesn't matter. As long as you have the first 3 having the same direction, either up or down, and then the fourth one does have to go into one of these and go in the other direction. So there'd be up, 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 down. It could be up, 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 down. So there'd be 2 electrons here. Again, these are all what are called energy degenerate. So you put 1 in each, and then wherever you put the 4th electron, it would have a down arrow, and it could be in any one of these. Does that answer your question?
Yes, thank you.
Any other questions?